Okay. So these two are the accept states. You might have AB. That's the A. That's the AB. And so you loop back to here. And then, so if you have all the states belonging to your F, your accept states, if you have them looping back to the start state of your NFA, that will give you the star. That will give you the result of the star of your NFA. Right? So there it is. There's in other words, that is the NFA that's equivalent to this regular expression. Right? So that was our first example. Now, second example, it's here it is here. Here's your regular expression. Okay? So it's a bit more complicated. So this sort of thing here we've just done in the previous example. It was example 1.56 in the text. This is example 1.58. You may wonder what happened to 1.57. Well, I think that was the figure number of this figure. It doesn't really matter. It's just these numbers are just useful for linking. When you're referring back to something, it's easy to find the something. Just because these numbers are here are what I call globally ordered. Alright, okay, so here's the second example. Here's your regular expression, and we're asked to convert that into a corresponding NFA, the machine, the automaton. Some minor pieces omitted. It's not all, well, some of the details, diagram details are missing. Okay, so here's your input symbol A, there's the corresponding NFA, we did that in the previous example. Similarly for B. Now A union B, now to do the union, the usual trick, you split it into two branches using epsilon arrows. Okay. Now it's A and B. Now that's the NFA that corresponds to an A. Here it is here, right? So you sort of see the general idea. To build up, to construct a more complex NFA, you use smaller NFAs. You put smaller NFAs together, sort of like Lego constructor kit. You build bigger parts by using smaller parts. So now it's the same thing with your regular expression, right? Like A union B uses A and B. Like these are your smaller, in fact smallest regular expressions, and you put them together to get A union B. Right? Well, similarly, you put the corresponding NFAs together to get the machine that corresponds to A union B, and there it is. Okay. Now now here's another part, ABA. Now remember, this is the total, the complete regular expression we're trying to find the corresponding NFA for. Right? So here's another part of it. That's this part. So what's its NFA? Well, we've done AB, so that would be sort of to here. Right? Well, you've got another A, so you do this again. Again, same question. Why are these epsilon arrows, transition arrows here? What are they for? Why not just go A, B, A directly? Why these? Okay. Now, so we've got the NFA corresponding to A union B. Here it is here. Now we have to start. Okay. So we do the same kind of trick here. So we loop back with epsilon arrows from the accept states. Okay. And we did this before in the proof of the completeness of the star operation, right, in earlier sessions, earlier boards. Okay, so this is the NFA that corresponds to this regular expression, and now now this is a concatenation. Right? So now I concatenate this. In other words, this NFA we concatenate it with this. And how do you concatenate? How do you concatenate? You use epsilon arrows from the accept states to the start state of the second part, like the y, like a concatenated string xy. So this, like that. Well, all this that would be your x correspondingly, and that here would be your y. So to concatenate x and y in terms of NFAs, in terms of the automaton, we did this for concatenation, proving that the regular operator concatenation is that, well, if you use that operator on regular languages, it's closed. Okay, so you construct epsilon arrows from the accept states of the x part of your xy, right? So those epsilon arrows then connect to the start state of your y string, so to speak. Right? So here, there are your epsilon arrows connecting to this, and that whole thing is the NFA that corresponds to this regular expression. All right. Okay, so that's the end of that session. Now, next session, we've given our two examples of finding the corresponding NFAs for regular expressions. They were examples of the if part of the proof. Theorem 1.54, wasn't it? Yeah, theorem 1.54, which is an important theorem. Now, the next board, we'll go the other way. We'll prove the only if part, and typically in an if and only if proof, one of those two parts, the if or the only if part, is harder than the other, and that's sort of a priori to be expected. It's unlikely that they'll be of equal difficulty. It's much more probable that one of them will be harder than the other, and that's the case also for this proof, 1.54, that theorem. Now, so the second part, the only if part, and that's Sipser calls that lemma 1.60, so that'll be the topic of the next couple of sessions, in fact. And it's harder, right? And to prove it, we introduce a new concept that I was mentioning in the first session, called the generalized non-deterministic finite automata, a GNFA. And as I was saying a bit before, what's significant about GNFA compared to an ordinary or just an NFA is that with a GNFA, along the transition arrows, you can have not just input symbols, you can have regular expressions along the transition arrows. Right? So we'll use that concept to help prove the only if part of this theorem. Okay, so I don't want to say too much because I'm stealing the content of the next session or two.